Let's find out the second variable, the one related to the angular momentum as action. So let's go back to the generating function and take the derivative of this with respect to JB. So JB appears on both the second integral and the third one. So I need to consider both of them. Taking the derivatives of these square roots, we have, so these are two different quantities. Let's call them C1 and C2. C1 is the theta integral and C2 is the R integral. Let's do the theta integral first. We can integrate it in the same way that we integrated the integral in phi. We extracted the JB from the denominator and write it in terms of the cosine of the inclination. Now multiplying and dividing by sine of theta. And now we need the geometrical change of coordinates from theta to another coordinate to solve this integral. So we go back to the geometry of the problem, and we're going to use the same triangle. But notice that now the hypotenuse of this spherical triangle is the side here, eta, which is the side that goes from the ascending node to the body. Now, remember that the argument of the periapsis went from the line of nodes to the line of apsides, right? That's the argument of periapsis, going from the line of nodes to the line of apsides. And then from the line of apsides to the body, you have the true anomaly. That's this angle that is being shown here. We're not putting here where the line of apsides is, but we have the line of nodes. So this side is going then from the ascending node to the body. So therefore, this is the argument of periapsis plus the true anomaly. So this is the triangle. This is the inclination I. This side is 90 minus theta. And opposite the right angle, you have this angle eta, which is the argument of pericenter plus the true anomaly. Using the law of sines here, you have sine of 90 minus theta over the sine of the inclination is equal to sine of omega plus f over sine of 90, which is equal to 1. So the relationship we have is cosine theta is equal to sine of the inclination times the sine of omega plus f. Let's call this eta. Now, if we take the derivative of this expression, then we have minus sine theta d theta is equal to sine I cosine eta d eta. Plugging that back into the integral, we substitute the numerator by this expression, and now we need to eliminate the sine of theta from the denominator. Well, we have the expression for the cosine. So if we square this, and if we take 1 minus this quantity, 1 minus cosine is, of course, the sine. So we substitute this into the integral. Substitute now this 1 here by cosine square of the inclination plus the sine square of the inclination. And extract now the sine is going to cut to this sine here, leaving cosine eta d eta, square root 1 minus sine square of eta. This square root is, of course, the cosine. So there you have it. C1 then is the integral of d eta, which is then eta. That's the argument of pericenter plus the true anomaly. Okay, so save this result. And let's solve now the second integral, the C2. Right, for this, let's substitute the energy. The energy is minus mu over 2a, and the Keplerian potential is minus mu over r. And let's substitute also the action JB by the angular momentum. Remembering also that the angular momentum is, what we have then is the angular momentum L times the integral then of 1 over r squared. That multiplies minus mu over a plus 2 mu over r minus L squared over r squared, the square root of this, and integrating the r. And instead of having divisions by r, let's extract this. These are squares also from the denominator, so that the integrand becomes, substitute the angular momentum by its expression in terms of the orbital elements. The angular momentum is the sum of major axis times mu times 1 minus the squared eccentricity. And substituting here in this last term in the denominator, that then becomes, so we remove that last mu. Now we can replace the equation of the orbit. Remember, the equation of the orbit in terms of the eccentric anomaly is r is equal to a times 1 minus z cosine of the eccentric anomaly. Therefore, the derivative is sum of major axis times the eccentricity, sine of the eccentric anomaly, if we make these substitutions, and if you expand this denominator, what is inside of the square root, you have minus a multiplying 1 minus 2e cosine big E plus e squared cosine squared of e plus 2a minus 2e cosine e. minus a plus a e squared. So let's distribute here this semi-major axis. Now I have minus a, and 2a, so this cuts. Oh, there was a missing a in this term. So 2ae cosine of the eccentric anomaly also cuts on both sides. The only two terms that are left are these ones in here. Therefore, the argument of the square root is ae squared, 1 minus e cosine square of the eccentric anomaly, which is, of course, ae squared times the sine square of the eccentric anomaly. Then eccentricity times the sine of the eccentric anomaly cancels on both sides. You end up with something much simpler then. Now, in order to continue, remember that we derived earlier the trigonometric transformations between the eccentric anomaly and the true anomaly. Particularly for the sine of the true anomaly, we had that being equal to 1 minus square root of e squared, cosine of the eccentric anomaly, times 1 minus e cosine of the eccentric anomaly. Now, the denominator is the same on both. So this is kind of looking like the quantity that we're trying to find. We have this expression for the sine of the true anomaly and another expression for the cosine of the true anomaly. Now, if we take the derivative of the first expression, the one for the sine, then we have cosine of f df, and use the quotient rule on this. You have, now this middle part here is the cosine of f, divided by an extra 1 minus e cosine e. So this is 1 minus the square root of e times cosine of f d over 1 minus e cosine big E. So the cosine of f cuts on both sides, and we can write it then dE in terms of df. dE is equal to the differential of the eccentric anomaly then is 1 minus e times cosine e times df over the square root of 1 minus the square of the eccentricity. Substitute that into the expression that I have for C2, and then I have angular momentum over A times mu. 1 minus z times the cosine of the eccentric anomaly cuts. It's both on the numerator and the denominator. And the eccentricity then, being constant, is removed from the integral. And what you have simply is the integral of the true anomaly. Now substitute again the definition of the angular momentum, and the denominator and the numerator cancel. The numerator is the angular momentum. Therefore, you have the C2 is simply just the true anomaly. I forgot a minus in here because there is a negative sign here on the JB. So when you take the derivative, it would be minus 2JB here on the numerator. So that will lead to a minus, and therefore this is minus C2. So we found our angle, theta B, was equal to C1 minus C2, which is W plus F minus F, which is omega, simply. So theta B is the argument of pericenter. And this is again constant because the Hamiltonian does not depend on JB. The associated Hamiltonian equation for theta B, the derivative of the Hamiltonian with respect to JB is equal to 0. So in the two-body problem, the argument of the pericenter is fixed. The orbit does not precess. So we found that the longitude of the descending node is constant, and the argument of periapsis is also constant. That means that in the two-body problem, the line of nodes is constant and the line of apsides is also constant. We update our list then of angle action variables. We had that for the action being LZ, the vertical component of the angular momentum, the associated canonical conjugate angle is the longitude of the ascending node. And if the action is the total angular momentum, the associated canonical angle is the argument of pericenter. So let's get to the last angle action variable.